and welcome to this video. This is the AQA Group 7, the halogens video. This is for revision purposes, so it's just a quick overview of the Group 7 topic. My name is Chris Harris, and I'm from AlleryTutors.com. And basically, like I say, we are going to have a quick look at this. This is very specific to AQA. The PowerPoint that I'm going to use here, you can use, and you can actually purchase from by clicking the link in the description box for this video. So if you just click on that, you'll be able to get a hold of it, and you can use it for revision, and you can use it for whatever you want, print them off or whatever. So yeah, so basically if you like what you see here, then you can get them for yourself. Okay. Also, like I say, these are tailored specifically to the AQA specification, and so obviously the spec points are reflected there for this topic. Okay, so we're going to start with the halogens, obviously, because this is all about Group 7. And obviously, the halogens are made up of non-metals. They're on the right-hand side of the periodic table. On the top of the halogens is fluorine, which is a pale yellow gas, and it has that electron configuration, 1s2, 2s2, 2p5. Make sure you can give the electron configurations of these. You should be able to do it for the elements such as fluorine and chlorine in particular. Chlorine gas is pale green. It's Cl2, and there's the electron configuration for it. Bromine is a browny orange liquid, and iodine is a grey solid. And you can see the electron configuration there is much longer for iodine, but it's just to kind of give you an idea. Okay. Now, generally, as we go down the group, starting from fluorine down to iodine, the boiling points increase as we go down the group. It's because the molecules and the size of the atoms and the molecules here, well, these are molecules, and the relative masses of them are getting larger. So therefore, we have larger van der Waals forces, and so this means that you need a higher amount of energy to turn these into a gas. Now, you can see some of these are obviously in different states. The top two are gases. Bromine is a liquid and iodine is a solid. So that basically just explains that the van der Waals forces are increasing, and at room temperature, as we go down the group, they become more solid. The electronegativity decreases as well. So when we bond these halogens to, say, like a carbon, for example, or another element in a covalent bond, then the electronegativity decreases. Now, the reason why is because the ability for one of these atoms to attract electrons towards itself weakens. The atoms get larger, and the distance between the positive nucleus and the bonding electrons increases. And basically, we have more shielding, so we have more shells between the nucleus and the outer electron. So that means it's easier to the electronegativity is a lot less for that reason. Okay, right. So let's have a look at some displacement reactions. Now, these are pretty important. You do see a lot of these for halogens, and they pretty much explain the reactivity that we've described before. And the fundamental rule is that more reactive halogens will displace a less reactive halide ion. So basically, like we said before, the reactivity in halogens, they decrease as we go down group 7. Okay, and so for a reaction to occur, basically an electron is gained, and we form that halide ion. Atoms with a smaller radius, they attract electrons better than the larger ones. So that's quite important. Basically, halogens are less oxidizing as we go down the group. So remember, oxidation is the loss of electrons. So they become less oxidizing as we go down the group. We can show this by reacting halogens with the halide ions. Okay, so halogens will displace a halide from a solution if the halide is lower in the periodic table. So we're going to look at these two here. Okay, we're going to look at all of these, in fact, and we're going to look at the reactivity of the halogen and the reactivity of the halide ion. So remember, as we go down the group, the halogens, the reactivity of them decreases. Okay, so let's look at the first one. Now, because these are two chlorines, chlorine water, Cl2, and chlorine, KCl chloride, which is KCl, potassium chloride, because they're just as reactive, we get no reaction. This one, though, we do. Chlorine is more reactive than a bromide ion, so we do get a displacement reaction. You can see here, there's the chlorine, there's the bromide ion. These react, and we get a displacement. So we get chloride ions, and bromine is made. So we get an orange solution being formed here, and that orange solution tells us that actually we're making a bromine solution here. Okay, looking at the next one, again, chlorine is more reactive than iodine, or than iodide, should we say. So we do get a displacement reaction. Now we get a brown solution. Iodine, when it's in solution, goes like a browny colour. So this brown solution is made of iodine. Chlorine, again, reacts with the iodide ions. There it is there. We get displacement. Chloride ions are made. An iodine solution is made. An iodine solution is brown. Remember, iodine as a solid is grey, but your iodine solution is brown. Okay, so look at bromine water. No reaction here. Bromine is less reactive than chloride ions, so we get no reaction. And no reaction for this one as well, because that's bromine react with bromide, so they're both just as likely to react. But the final one, again, we form our brown solution. Again, it's the same reason. Bromine is more reactive than iodide ions, so we get a displacement reaction. We form 2Br-, and we get iodine produced as well, and obviously this is in solution, so it makes it turn brown. And the last one, it's no reaction here. Again, iodine is less reactive than chloride, so we get no reaction. Iodine is also less reactive than bromide, and then obviously iodine and iodide are just as equally reactive, so they won't displace either. So yeah, make sure you know your half equations and you know the colours and you know the reasons why. It's all about this displacement. Okay, right. Bleach. Okay, so there wouldn't be halogens without talking about bleach, really, let's be honest. So this is made by using a disproportionation reaction. Okay, try to say that one quick. It's basically a reaction where we're getting oxidation. An element is simultaneously oxidized and reduced, as we'll see in a minute. I'll show you the reaction. But if we mix chlorine and sodium hydroxide together, okay, we'll form sodium chlorate 1 solution, and this is known as bleach. Now the reaction, like I say, as you can see here, is the sodium hydroxide plus chlorine. Literally, that's what it is. Sodium chlorate 1 is this stuff here, NaClO. Okay, so that's that one. Plus you form your salt and you form water as well. Okay, so really important. This is your bleach. That's bleach there. Okay, so let's look at this disproportionation thing again. Chlorine is an oxidation state of 0. It's an element. Chlorine here is +1 because oxygen's -2, sodium's +1. So for the whole thing to be neutral, chlorine must be +1. And chlorine here has an oxidation state of -1 because sodium is +1. So chlorine has been simultaneously reduced and oxidized, like I say, and we call this a disproportionation reaction. And we can use bleach. Bleach is pretty useful, obviously. We can use it to treat water. We can bleach paper and fabrics, so we can make paper whiter or fabrics whiter. And obviously we can use it as a cleaning reagent. Obviously you put bleach, use it in bathrooms, cleaning toilets, etc. So yeah, it's got a pretty important use. Okay, another important use is obviously water sterilisation. Now without this, we would have had outbreaks of cholera, and actually in some countries today where they don't have efficient water sterilisation techniques, they unfortunately do get spreads of cholera, which is a waterborne disease. But the whole point of adding chlorine to water is to kill the bacteria in the water, including diseases, including microbes, that cause cholera. So yeah, adding water to chlorine will produce chlorate ions, ClO-, a little bit like the bleach that we've seen just before. These kill bacteria and they're useful in drinking waters and swimming pools. So let's have a look at these again. Now this is slightly different. Again, we've got water and chlorine, no sodium hydroxide. We're using water instead. And what we form is H+ ions, Cl- ions, and ClO-. Now you might also see this as HCl and HClO. So these H+ can be attached to this, but because they're soluble and it dissociates pretty strongly, then we normally write them as separate ions. But again, if we look at our oxidation state, chlorine has an oxidation state of 0, obviously -1 here and +1 here. So again, this is a disproportionation reaction. The chlorine at the start has been simultaneously reduced and oxidized. Okay. Now, this is quite important, especially in things like swimming pools, because sunlight can decompose chlorinated water too. And the problem is that we get no ClO- that is made. And remember, it's the ClO- that actually kills the bacteria. So if we look at these two here, let's have a look. We've got water and we've got chlorine. Now, if we have sunlight that's present, actually what we produce is 4H plus, Cl minus, and O2. Obviously, this can pose a problem in swimming pools because if you get sunlight like bleaching into the side of the building, maybe is where the swimming pool is, the sunlight can actually destroy the bleach that's used in swimming pools, the ClO minus, and what we form is Cl minus and O2. Now, obviously, because we don't have any ClO minus because the sunlight has broken it up, then obviously we don't have any active ingredient to kill the bacteria. So this is why the chemical reagents or the chemicals that we add to swimming pools have to be replaced quite regularly, because sunlight breaks them down into these compounds here, which are obviously different to that bleach up there. Okay. Drinking water. Okay, so advantages and disadvantages. Obviously, it's in the UK and we do chlorinate water, but there are, like with anything, adding any chemical to anything, there's advantages of doing it and disadvantages, and you need to know what they are. So the advantages, they destroy microorganisms that cause disease, so that's a pretty good thing. They're long-lasting, so they reduce bacteria buildup further down the supply, which is pretty useful, and reduces the growth of algae that discolours water and give it a bad smell and taste. Last thing you want coming out of your tap is brownish water that doesn't smell too good. It would put you off pretty much. So yeah, basically the chlorine helps to reduce that. But the disadvantages, chlorine is toxic. We can't hide that. And it can irritate the respiratory system. So people who add this chemical into the water have to take obviously precautions when adding this in. Liquid chlorine causes severe chemical burns to the skin. So if there was high levels of chlorine in drinking water, that could obviously cause problems, but there's systems and safeguards from doing that. But I suppose the biggest one here is the fact that there is this belief by some people that or some scientists that the chlorine could react with organic compounds that are present in the water, and they make chloroalkanes, and these have been linked with causing cancer. But obviously the risk of not chlorinating the water and could lead to what, like we said before, cholera epidemic, and cholera is lethal as well. So basically what we're saying here is the advantages outweigh the risks, or the benefits outweigh the risks. In this case, the levels of chlorine that are added to water are very, very, very small, and scientists believe that the risk of cancer from this is obviously very low, incredibly low, because of the low levels that are added anyway. They only add just enough just to make sure that the bacteria is killed in the water. Okay, so right, let's look at these halide ions. Now these are quite difficult actually, these things. So we've obviously looked at halogens so far. We looked at a little bit of the halide ions with the displacement reactions, but halide ions already have that electron already. Now these lose that extra electron they've got, and so this makes them really good reducing agents. Okay, so remember, reducing agents are oxidized themselves. Okay, and oxidation is the loss of electrons. So halide ions lose electrons because they've got that extra one, and so they make some good reducing agents. Okay, so basically as we go down the group, the ionic radius increases, and I've just drawn that diagram there. Basically the distance between the nucleus and the outer electrons becomes larger. There's more shielding. Use all these words in your exam. And the attractive force gets weaker. Okay, so it's not as strong. And the outer electron is lost a lot more readily. And this is the reason why I minus is more powerful reducing agent than F minus. So I minus loses that electron much more readily than F minus. Okay. Now there's two tests you need to know. Okay. To prove this trend. So one's with sulfuric acid, which we'll look at next, and the other one is with silver nitrate solution. And you've got to know the results of both of them. And I think the most difficult one is the one with sulfuric acid, because you get a lot of equations here. So let's just talk it through, make sure you know what's going on. Okay. So some halide ions can reduce concentrated sulfuric acid. So that must be concentrated. That's very important. So what I'm going to show you here is basically a little kind of, it looks a bit like a train map, I like to call it. I think it's probably easier maybe seeing these things in this way rather than in other ways that I've seen in some notes and sheets and books, etc. I think this probably is an easier way of doing it, but you can use it however you want. Basically what I've done is I've written my reduction products of sulfuric acid on the top row. The only one which isn't a reduction product is this one, sodium hydrogen sulfate. But these ones are reduction products, and I'll come on to these in a minute. And then what I've done is I've looked at sulfur, okay, because sulfur is the key element here. And I've written the oxidation state of sulfur underneath. So we've got +6 here, +4, 0, and -2. And what I've done is I've written our halide ions down here. These are the halide ions that we're going to be using. We're going to react it with concentrated sulfuric acid. So we're going to react a chloride ion with concentrated sulfuric acid and see what products we produce. We're going to react a bromide ion with the same stuff, see what products we produce. We're going to react an iodide ion, see what products we produce. Okay, so let's start with the first one. Okay, here's our underground train line thing. Right, so we're going to look at A. Okay, now the good thing is that chlorides, bromides, and iodides, they all produce this compound here, sodium hydrogen sulfate. And we need to know the reagents of these as well, the reactions of these. So this is point A. Now point A, this is not a redox reaction. Okay, this is just a standard chemical reaction between a salt and an acid. So here we are. This is with sodium chloride, sulfuric acid, react with sodium chloride. All we get is one of the hydrogens is given up to form HCl. You get white misty fumes here, and you form sodium hydrogen sulfate. You also get the same with sodium bromide and sodium iodide as well. However, as you will see, that these reagents here, these sodium hydrogen sulfates, will then go on to react further. So actually, you have very little of these anyway in the overall reaction. But certainly with the chloride, the only product you get with sodium chloride is that, and that's it. You can see the arrow stops there, no more product produced. Okay, so now we're going to bring our attention onto bromide. Okay, so bromide is, let's have a look. Okay, so these are going to be looking at reaction B. So bromides can actually reduce further the sulfur further. They can reduce it to produce sulfur dioxide, and iodides can do the same as well. Okay, so they can produce sulfur dioxide. So let's have a look at their reactions. So this is point B. Okay, and you can see in addition to A as well. Okay, so we've got obviously all the A reactions as well. But with sodium bromide, because that's what we're going to look at mainly, we get the same reaction with sodium iodide as well. What we do is we write down our half equations first, okay? The bromide is being converted into bromine. I've written the half equation there, so the bromide ions are being oxidized. Br minus going to Br2, obviously we balance it with 2 electrons, okay? This is being oxidized. I must stress as well, if you don't know how to work out your half equations, you really do need to know how to do this. I have put a video on that describes how to balance half equations. You've got to know that as well. I'm just going to go through it as an overview here, assuming that you know how to do it. But this is the bromide ion, and then crucially, this is this bit here. We're starting with sulfuric acid, and we're going to produce sulfur dioxide because that's one of our products. What we do is we balance with water first, then protons, then electrons. Okay, so we'll just balance this half equation. This is the sulfur being reduced. Okay, so this is a redox reaction because we've got oxidation and reduction. Cancel out our electrons and combine the equations, and we should get an overall ionic equation, which is this here. So you can see the sulfuric acid has been reduced to sulfur dioxide. We should see in this reaction an orange vapor of bromine being produced, and that tells us that actually this reaction has occurred. Okay, so bromine tells us that we have produced sulfur, we produced bromine, and we've also produced sulfur dioxide as well, which is a choking gas. Okay, let's go further. So bromides are not as powerful reducing agents, so they can't reduce that any further. But iodides can. Okay, so they keep going. So iodides can reduce sulfur even further to produce sulfur, which is this sulfur solid. Again, we're going to do the same thing. Look, balance it out. 6I minus I2. So we're going to put I minus going to I2. And then we basically try to balance that out. We do the same here. Start with sulfuric acid forming sulfur, and then we balance with water, protons, then electrons. When we balance this, we effectively worked out that we have to multiply the top one by 3 so we can balance out the electrons, the 6 electrons. Remember, we've got to try and balance these out. Cancel them out, rewrite out the equation. The overall equation here is obviously I minus going to I2 and sulfuric acid going to sulfur, so producing a solid sulfur. And iodide ions are so powerful at reducing, they reduce the sulfur even further, and they produce H2S. Okay, I should point out with this one as well, you produce sulfur solid, which is yellow. So this one, the final step, is step D. Again, same thing. Look, we're just going from I- to I2, just balancing out. Sulfuric acid this time, we're forming H2S, hydrogen sulfide, we call it, which is this one here. And the overall ionic equation, obviously, just like before. Again, we've got to multiply this top one by 4 to make sure we get 8 electrons on both sides. Classic one here, rotten egg smell. H2S is a nerve agent. It's really toxic. You shouldn't be breathing this in. And it smells of rotten egg. It's got a horrible smell. It's also known as sewer gas because it's found commonly in sewers. So you probably get an idea of what they may smell like. Okay, so that's your reaction with halide ions with sulfuric acid. Make sure you can balance your half equations. Really, redox is crucial here, being able to balance them. Okay. The other one, which is probably a little bit safer to use, let's be honest, is reacting it with silver nitrate. Okay, so we can use these halides, add silver nitrate, and we can confirm further with ammonia, which we'll look at later on. Okay, so this is how we do it. We test for chlorides, bromides, and iodides. All we do is we add nitric acid first, dilute nitric acid, then we add silver nitrate solution, AgNO3. The colour of the precipitate will help you identify the halide ion. Okay, so I'll come on to the nitric acid a little bit later on as to why we add that. But you can see here we've got the test tubes. We've got different coloured test tubes. Now this one here is the white test tube. White precipitate is formed. This is chloride ions. Okay, so we add silver nitrate, and if we get a white precipitate, that's a chloride ion. This is the reaction that happens, the half equation. Ag plus Cl minus forms AgCl. The cream one here is a sign of bromide ions, cream precipitate formed. The cream precipitate is silver bromide, that's the actual precipitate. And here's the ionic equation. Ag plus Br minus forms AgBr, silver bromide, which is a solid. And the last one, the yellow one, is iodide ions. Now these form a yellow precipitate, and here's the half equation for that as well. The ionic equation, of that. Ag plus I minus forms AgI. Silver iodide is your yellow precipitate. Okay, the nitric acid bit that we mentioned here, this is important that we add this, because what this does, it reacts with any other anions that could, and any other halides, for example, for like we're looking at carbonates, that could precipitate out as well, and when they react with the silver. Now, this could give a false result, because obviously we could get silver ions reacting with any, like carbonates, and we could get precipitates forming, and we might think, oh, we've got a chloride there, but actually we don't, because it's just reacted with an impurity. So we just basically add the nitric acid just to mop up these kind of rogue carbonates that are floating around in the water naturally. We can also test this further as well. And because these are really difficult to see, I mean, obviously we can see them side by side here. We've got a white screen behind here, but it's really difficult to tell in isolation. So we can do a further test. We add ammonia to each one of these solutions. So basically we add dilute ammonia to each of these, and the chloride one should dissolve. The precipitate should dissolve with dilute ammonia. Then, obviously, we know that's got to be chloride, so we put that to one side. We should have these two left. So then, if we add concentrated ammonia to these two that's left, the concentrated ammonia, your silver bromide should dissolve in concentrated ammonia, but your silver iodide shouldn't. It's insoluble. So, bromide, you get a cream precipitate, dissolves in concentrated ammonia, and iodide ions, the yellow precipitate, is insoluble, so it doesn't dissolve. So, really important, make sure you know these little reactions, and you know the colours and what they're testing for, and obviously the further test with ammonia as well. Okay, just the final little bit really, because obviously we're looking at ions here, and I thought it would just be good to kind of look at some of these other tests. So, for example, we can test for group 2 ions, and we can use flame tests. Basically, we take the solid sample, you put it on a nichrome wire, and then you put it into the Bunsen flame. We can spray it on as well. But it's a problem if your compounds are insoluble. Obviously, we can't dissolve them in solution, so we can't spray them. But the idea is that, like I say, you put it in nichrome wire, dip it into hydrochloric acid to just clean the wire, dip it into the sample, place the loop into a blue Bunsen flame, because it must be blue, and observe the colour. The colours that you need to know are calcium is dark red, strontium is red colour, just normal red colour, and barium is a green colour. Okay, so as long as you know these colours here, that's quite important. Okay. More test for ions, ammonium compounds and hydroxides. Basically, we can use litmus paper for these. So, testing for ammonium compounds, what we do is we add sodium hydroxide to our ammonium compound or suspected ammonium compound, gently heat it. If ammonium is present, you'll produce ammonia gas. And all we do is we use a bit of damp litmus paper, red litmus, and it'll turn blue if ammonia gas has been produced. Here's the overall reaction. Look, ammonium ions plus hydroxide ions will produce ammonia plus water. Okay, and testing for hydroxides, basically these are alkaline and they'll turn red litmus blue, which is pretty straightforward. But it's really difficult because a lot of things turn red litmus blue. It's not necessarily a sign of a hydroxide. So you're going to do further tests to effectively discount the other ones and just to confirm that it is a hydroxide. Okay, more tests for ions. So carbonates and sulfates using hydrochloric acid and barium chloride. So this is a little bit of a mixture of group 2 as well. So test for carbonates, dead easy. All we do is we're going to add an acid to a carbonate. So hydrochloric acid, if we think it's a carbonate, if we add it to a carbonate, we should get carbon dioxide gas given off. And then obviously carbon dioxide, the gas given off, we can test for carbon dioxide, bubble it through lime water and it will turn cloudy. Okay, testing for sulfates. We've seen this already in group 2, but just to kind of recap this. So basically, if we need to find out if something contains sulfite ions, all we do is we add hydrochloric acid. It just removes any carbonates in there. Again, we don't want to see them because they could give a false result. And then all we do is we add barium chloride to the solution. And if there is sulfates present, we should see a white precipitate formed. And this white precipitate is barium sulfate. And obviously, as you may know, barium sulfate is insoluble. So that's why we see this precipitate. Here's the ionic reaction here. Barium 2 plus sulfate ions forms barium sulfate. There's your solid. Look at your state symbols. Aqueous, aqueous, solid. That means precipitate is formed. Okay, and basically the final thing is just make sure you test these things in a particular order. Just be methodical with your practical technique. And this just prevents any misconceptions or false positives. So the first thing really you should do is test for carbonates first. That'll basically tell you if you have got any carbonates in there. Obviously add your acid. If there is carbon dioxide produced, brilliant, you've just identified a carbonate. If there isn't, then you need to test for sulfates. So basically take your sample, add barium sulfate to it. Do you get a white precipitate formed? If you do, fantastic, you've got a sulfate. If you don't, you go on to the final test, and this is basically testing for your halides. You add your silver nitrate solution, remember, and your nitric acid to mop up any rogue carbonate ions that may be floating around. Test for halides, white, cream, yellow, and then add ammonia. Dilute will dissolve your chlorides, concentrate will dissolve your bromide, salt, and iodides don't dissolve. So then test for your halides. And basically doing it this way means you can be certain that, or you try and narrow down what compound you've got. And that's it. So that's group 7. Hope that was pretty useful. It's just a very quick overview, really, of the topic. Like I say, if you want to purchase these PowerPoints that could be really useful for your revision, then if you just click on the link in the description box below the video, and you'll be able to get them there. All right. Thanks very much. Bye bye.